and it's going to just look at it a slightly different way because it's bases, okay? There are a couple slides left on acids. Yeah, there's a couple slides left on acids. Polyprotic acids. Let's just dissect that word. What does polyprotic mean? What does many protons, and what is synonymous with proton around here? H plus, not hydrogen. H plus, right? So these are acids that have more than one ionizable proton, okay? Ionizable hydrogen. For example, H2SO4. Sulfuric acid has 2 ionizable protons, right? Here's what you need to know. They can only ionize one at a time, okay? So H2SO4 will ionize its first proton. What's the conjugate base of H2SO4? HSO4 minus, because it gets rid of a hydrogen. It was 0. It gets rid of a positive, so now it has an extra negative, right? Okay. Then it can get rid of that second hydrogen. So HSO4 minus still has the ability to donate a proton, right? So it too is an acid. It's not a strong acid, it's a weak acid. It can donate a proton. What's the conjugate base of that? SO4 2 minus, which is also known as the sulfate ion. Okay? SO4 2 minus is the sulfate ion. So if you work on memorizing the polyatomic ions and the strong bases and the strong acids, it's all going to go together. Okay? A lot of those polyatomic ions make strong acids. Okay. Here's the other thing you need to know. The Ka value is different for each proton that's being ionized. So if an acid is a polyprotic acid, the Ka value for the first one it gives up is different than the second one it gives up, and if it has a third one, it's different from the third one it gives up. Okay? Remember, Ka is a measure of what? Acid dissociation. So the higher your Ka, the more it's ionizing. Okay? It's usually the first proton that ionizes the most. Okay? Remember, H2SO4 is a strong acid, right? HSO4 minus is a weak acid. So that gives you an idea. Okay? All right. Here's a chart that just shows you that, what we just discussed. Okay? So you can see, like for ascorbic acid, how many hydrogens are there right there? 2. So they're showing you 2 acid dissociation constants. Which one's bigger? Which is called Ka1, right? Ka1 is bigger. Ka2 is smaller, okay? Look at carbonic acid. Also has 2. You can see the different values. Citric acid has how many? 3. Okay? And again, you guys, keep in mind for your organic compounds, okay? For your organic compounds, they're going to separate out the ionizable hydrogens from the ones that are like stuck in the compound, okay? So if only one of these was ionizable and the other 2 were stuck in the compound, it would have said HC6H7O7. It's the fact that 3 of them are separated out that gives you a hint, and they're on the end, that all of those are ionizable. Okay? All right. So you can see how that works. Questions about polyprotic acids? Okay. Now we're going to talk about weak bases. Okay. We're going to focus on ammonia today. I really wish I had another. I need Schoology. That's the problem. I can't. I know. It's all good. I just note to self for how to be on fire next year. 2 iPads. So, all right. We're going to talk about NH3, which is a weak base. Do me a favor. Remind me why NH3 is a good base. We've discussed this. What does NH3 do? What? Why does it make a good base? What does it have? Go back to our definition of bases and acids. Acids are proton donators. Bases are proton acceptors. What do bases need to accept the proton? They need an unshared pair of electrons. Draw ammonia for yourself real quick. Draw it out. Draw NH3. Okay? I'll give you a second. Okay. What does NH3 have on the nitrogen? Huh? A lone pair. Okay. So that's a good place, remember, for hydrogen to bond to. Okay. That H+. All right. Now, because we're looking at bases, we're not going to call it Ka this time. We're going to call it Kb because we're looking at the base dissociation constant. Correct? Okay. Now, look. I'm going to write on this board. Okay. Just look over here for a second. By look over here, I mean the Swivl. Oh, you're never going to see that. Whatever. Okay. I want you to work through this. If we're focused on ammonia, you guys, and that's our base, we need to write the balanced equation. Tell me, who's ammonia reacting with? Water, right? Think about how we did our weak acids. What was our other reactant always? Water. Okay, remember, like last time we did acid plus water makes products. Okay, in this one, water is going to serve as our acid. I think that's useful because you have to think about what it's going to do. What do acids do? They donate a hydrogen. So and bases accept. So what is this going to become? NH4+. And what are we going to be left with here? OH-. Okay, that's a little important. It's going to look a little different. We're not looking for H+ anymore. H+ is the marker of an acid. Remember, go back to that original definition of bases. Bases are something that increase the hydroxide ion concentration in solution. How does it do that? Because when we say in solution, we mean mixed with water. Water serves as your acid. Water donates a hydrogen, so you get your conjugate acid, and water becomes your conjugate base, which is the hydroxide ion. The conjugate base of water is the hydroxide ion. That's how ammonia, that does not appear to have any hydroxide in it, is a base. Because it reacts with water, water serves as the acid, you end up with OH minus as a product. But it's important for you to understand that, because it's going to flip how we're looking at things in our ice chart. Because if I make an ice chart here, do I have H plus in my ice chart? No. So when I get down to my equilibrium concentration of OH minus, what is that going to allow me to find? POH. And then can I find pH from there? Yes, because what's the relationship between OH and pH? They equal 14. Do you understand that this is all coming together? Okay? So, like base questions, weak base questions, great questions to ask on the AP exam because it covers everything. Right? Okay. So we're going to look through the example that's in the notes. All right. I'm going to go through it somewhat quickly. What? Hold on. And then you're going to do an example, and then we're going to call it a day. Okay. Does this KB equation make sense? Does this equilibrium expression make sense to you then? Yes. Does the balanced equation? Are in there because it's a liquid, right? Okay. Great. There are two main types of weak bases. You don't really need to know that. There are also known base dissociation constants at 25 degrees Celsius. Okay, so there's also a table of those. Okay, so you can look them up. Okay, so let's look at this example. It says, what is the pH of a 0.15 molar NH3 solution? Okay, you with me there? Okay, fix your equation so that the E becomes a double arrow. We have enough battery life now. Okay, so there we go. So in this slide, okay, they're saying what is the pH? So pH equals what of a 0.15 molar NH3 solution? So they're using the same equation, right? So how can we find this? What do we do? Ice chart. Okay, so make your ice chart. Get rid of your water part. Where does the 0.15 go? Initial for NH3. What goes in initial for your products? 0. Okay. Do we know anything else?
Yes.
What?
I know KB.
We know KB. Is that going to help us fill in any part of our chart? No. The only other thing we know is we have a 1 to 1 to 1, which means what? They're all going to change by X. How are your products going to change? Plus X. How are your reactants? How's your reactant going to change? Minus X. 0.15 minus x, which is basically going to be 0.15. Okay? Now, Sierra, you're right. We do know Kb because we can look it up for ammonia, right? So what can we do here? Kb equals what? 1.8 times 10 to the negative 5. And how can we use that?
Do x squared.
Right. We can put it in to our equilibrium expression, use x for NH4 plus and OH minus. That is going to be x squared, but I just want to make it clear where it's coming from. And we're going to put 0.15 down here for ammonia, right? Now solve for x. Literally. Go ahead, solve for x. And you should get, right, 1.6 times 10 to the negative 3. But keep in mind, what is that? This is where it's important. This is where people tend to overlook the final step. This was OH minus, correct? So this is 1.6 times 10 to the negative 3 equals your hydroxide ion concentration. You have to go back to what the question's asking. What do? Take the negative log of this to get what? To get POH. So get that, get POH. Subtract that from 14. So what was your POH? What? 2.78. Remember, we typically go to the hundredths for pH. So 2.78, which means your pH was 11.22. Okay, good. All right. Okay. Go to page 693 in your book. It's also sample 1616, I think. Yeah. 693. It's sample exercise 1616. I don't know how you search. Like, do you search by page number? It's in section 16.7, and it's sample exercise 1616. And what I want you to do is practice exercise 2. Okay? So take a couple minutes here. And like really, this is challenging. Okay? Just try to get as far as you can. Okay? 693.
Oh.
You're doing practice exercise 2. And see how far you can get.